We are going to take a moment to talk about an important principle that underlies all of computing. Everything is a number. What does this mean? Computers can only work on numbers. They store all data in their memory as sequences of ones and zeros, which are binary representations of numbers. The processor, the brain of the computer, can only do mathematical operations like addition, subtraction, comparing two numbers to see which is bigger, and moving numbers to different locations. The processor can do this math really fast, typically billions of math operations per second, but it can really just do math. Accordingly, if some type of data does not seem to be a number, it has to be represented as a number. One type of data that seems like it is not a number is text. The slide that is displayed here has many words made up of letters and other characters like question marks, exclamation marks, commas, spaces, and others. All of these characters are actually just numbers to a computer. There's a specific mapping of characters to numbers called ASCII, where, for example, capital A is the number 65. Of course, you should generally not need to know the numeric values. You can just write down the letter, like quote A, and that represents the numeric value. Of course, since characters are numbers, we could do math on them. We could test if a letter is in a certain range, or add a value to it. Text is then just a sequence of numbers. There are a variety of important algorithms that use this fact to do math on text. One major type of algorithm is cryptography. When you visit a secure internet site, your computer does math on that data that it sends to the site to prevent anyone else from examining it or tampering with it between your computer and its intended destination. While we can make use of the fact that text is numeric when we need to, we do not have to think about numeric representation most of the time. Abstraction lets us avoid that level of detail and think and write code in terms of the text that we want. Our programming tools and languages take care of the fact that everything is a number. Another type of data that seems non-numeric is images. However, as with everything else, these are also made up of numbers. The fact that images are numbers allows us to have a variety of algorithms that work on them, ranging from how the image data can be stored efficiently to algorithms that analyze images mathematically and figure out characteristics of those images. The way that images are stored numerically is based on the idea of a pixel. A pixel is a tiny square of one single color. That color is then represented as three numbers, one for red, one for green, and one for blue. Those three numbers each range from 0 to 255. To see these pixels, let us consider this small region of the image of a kitten and zoom way in on it. Now you can see the individual pixels that make up this part of the image. If we pick out a few of these pixels, we can see that each is one color and look at the red, green, and blue, or RGB values that describe that pixel. You don't need to know specifically how to make a given color from RGB values, and we won't be doing anything with images in this course, but you will work with them some in the next course. For now, we wanted you all to understand how they are numbers. You might wonder why the everything is a number principle matters. After all, you can look at images just fine without knowing they are numbers. The first is that we want you to understand that all programming is programming with numbers. Sometimes, novice programmers ask a question like, "We're doing all this programming with numbers. When will we do programming with other stuff?" The answer is that it is all programming with numbers, and so all the same skill set. The other is that the fact that everything is a number means that computers need to know how to interpret these numbers and operate on them. This need gives rise to the idea of types. A type tells the computer how much space a particular piece of data needs and how to interpret and operate on the numbers that make that data up. Many languages have a static type system. Such languages are called strongly typed. In these programming languages, a tool called the compiler checks the program to make sure that certain type-related mistakes were not made. If the compiler identifies such a problem, it can report the mistake to the programmer, who can then fix it before trying to run the code. I personally love strong type systems and think that it's great that the compiler can find my mistakes and help me fix them before they cause problems. However, Python does not do static type checking. Instead, Python uses an approach called duck typing. Under this approach, type-related problems are detected when the program is run. The term duck typing comes from the saying, "If it walks like a duck and quacks like a duck, then it must be a duck." Put a different way, this saying means that if we need a duck, we're happy with anything that can walk and quack. In Python, this means that if my code says A plus B, then it does not matter if A and B are numbers. They can be any type of thing as long as we can do plus on the two types that they actually are. I want to note that the duck typing approach puts a bit more responsibility on you, the programmer. In a statically typed language, the compiler can catch certain mistakes. In a duck-typed language, you need to be more careful to not make such mistakes and test more extensively to find any mistakes you might have made. We will also note that duck typing introduces certain runtime overheads in terms of how long your code takes to run. In the next course, you will learn about NumPy, which can mitigate these overheads somewhat by providing arrays that are a single type.